In this section, we're going to talk about momentum. We're going to use P to represent it. Momentum is a measure of the amount of motion an object has. This is a measure of the amount of motion an object has. So on what factors does the amount of motion an object has depend? Obviously depends on the velocity. So it is proportional to velocity. It is proportional to its velocity. And if you've got two objects moving with the same velocity, the object with the bigger mass will have more momentum. So it's also proportional to the mass of the object. It is proportional to the mass of the object. Proportional to the mass of the object. Okay? So momentum is defined to be a product of mass and velocity. Okay? So that's the definition of momentum. P equals mass times velocity. Momentum is defined to be mass times velocity. Okay, so in this formula, this represents momentum. M represents mass, and V of course represents velocity of the object. Now let's look at the unit of momentum. Unit of P is obviously unit of mass, kilogram, times unit of velocity, meters per second. Okay, so the unit of momentum is kilogram meter per second. Okay, now let's look at an example. Let's say a 2 kilogram object is moving, let's say, with a velocity of, let's say, v equals maybe 2I plus 3j meters per second. Okay, the question is calculate its momentum. So momentum is a vector quantity, so we got P equals mv. That'll be 2 kilograms, and then times the velocity 2 in the I plus 3 in the j. Okay, so the momentum would be 4 in the I plus 6 in the j, and the unit of course is kilogram meters per second. Okay, and now there's another quantity used in relation with momentum. It's called impulse. So let's define impulse. Impulse, we're going to use I to represent it. Okay, this is defined to be the product of the force acting on object and the time interval during which the force is applied. This is defined to be the product of the force acting on an object and the time interval during which the force is applied, applied. Okay, so let's say an object is acted upon by a constant force in the interval time delta t, then the impulse would be the force times the time interval, right? If an object is subjected to a constant force F for a time interval delta t, then we can say impulse equals the force times the time interval. Right. Okay. So as you can see from here, the unit of impulse is the unit of force, Newton, times the unit of time, second. How about if the force is variable, which is the case most of the time, then we can take a small interval delta t, during which the force can be assumed to be constant, and we can call the impulse during that interval di, okay? So this would be force or impulse impact on the object during time interval delta t, and of course to get the total impulse we can integrate. All right, so this implies the integral of di equals the integral of f dt, right? This is of course the impulse, so you can say the impulse acting on this object is maybe from the initial time to the final time of the integral f dt, okay? So if the force is variable, then we have to integrate using this formula. All right, this is if the force varies as a function of time, then we have to use this integral to calculate impulse. Okay. Let's say example. Let's say an object, maybe let's say of mass, let's say 5 kilogram, is subjected to a force that varies with time, according to the formula. Let's say the force is maybe negative t squared plus 4, okay? Now the question is calculate the impulse impacted on the object, in the first 2 seconds, let's say, in the first 2 seconds. Okay, so of course this is a vector, let's say this is in the I direction. All right, so looking for the impulse, question mark, and the impulse is the integral of the force with time, okay? Therefore the force is this one, negative t squared plus 4 dt, and we're told in the first 2 seconds, so we're going to go from 0 to 2, okay? So this will be the impulse, so it will be negative t cubed over 3 plus 4t, okay, going from 0 to 2. All right, so it will be negative 8 over 3 plus 4 times 2, or 8. So it will be 3 negative 8 plus 24, or 16 over 3 Newton seconds. All right. Now we're going to look at the relationship between force and momentum. Relationship between force and momentum. Force and momentum. So we're going to start from Newton's second law. As you remember, Newton's second law implies the net force acting on an object equals mass times acceleration. Okay, and remember, acceleration is the rate of change of velocity with respect to time, right? So that from that it follows that force equals mass times the derivative of velocity with respect to time. Now mass is a constant, we can take it inside, that is mass times velocity with respect to time. But momentum equals mass times velocity, okay? So but mass times velocity equals momentum. So we have the following formula: force equals the derivative of momentum with respect to time. Okay, so this is the relationship between momentum and force. So in words we can say force is equal to the rate of change of momentum with respect to time. Actually, when Isaac Newton wrote the second law, he wrote it in terms of momentum this way. He didn't write in terms of acceleration. This is the way Isaac Newton wrote the second law. All right. Now, let's cross multiply. So we have dp equals force times dt, okay? Now if you integrate, so the integral of dp equals the integral of dt, okay? Let's say this goes from initial momentum, this goes final momentum, and this goes from initial time to initial final, okay? But remember, this integral over here equals p final minus p initial, or delta p. This is a change in momentum. And this one, if you remember, is simply the impulse acting on the object. So you've got the following formula: the impulse acting on object equals to the change in momentum, okay? So you've got a very simple relationship between impulse and change of momentum, okay? So in words, the impulse acting on an object, the impulse acting on an object is equal to the change in its momentum. Change in its momentum. Okay. Now we've seen that the unit of momentum is kilogram meter per second, and the unit of impulse is Newton times second. So both units should be the same, right? So let's try to prove that. So you've got Newton second. This is the unit of force, therefore equals kilogram times meter per second square, and then multiply by second, you get kilogram meter per second. So this unit is actually equal to kilogram meter per second. All right. Now let's look at an example. Maybe let me go to the other side. But let's say an object of mass, let's say 0.2 kilogram. Okay, let's say we have this is the wall. So let's say the object starts over here and then hits this wall, let's say with a velocity of 10 meters per second, and let's say this angle is 37 degrees, and then bounces back this way, okay? Let's say with a velocity, let's call this initial, final, which is maybe let's say 8 meters per second, and let's say this angle over here is maybe 53 degrees. Okay, so an object of mass 0.2 kilogram let's say hits the wall as shown. Let's say hits a wall as shown. Okay, so let's say calculate the change in its momentum. Calculate the change in its momentum. Okay, so we're looking for delta P, question mark. But delta P is P final minus P initial, and this one is minus times final velocity minus mass times initial velocity. So that's what we're calculating. So the mass we're told is 0.2 kilograms. The initial velocity is this one over here. The initial velocity is like this. Its magnitude is 10, okay? And then its direction is 37, so we can say it's cosine of 37 in the I direction and sine of 37 in the j direction. Okay, so this is initial velocity. So we've got cosine of 37 is 0.8, so it becomes 8 in the I direction, and then sine of 37 is 0.6, so that is 6 in the j direction. This is the initial velocity. Okay, now the final velocity, you see the speed is 8. All right, so this would be this 37 over here will be cosine of 37 in this direction, so you got 8. Of course in the I direction it's going to be negative. If this is 37 will be negative cosine 37 degrees in the I direction, and then this component of course would be sine 37. Oh, that's 53 degrees. I'm sorry, this is 53. No, I'm sorry, this is 53, this is 37, right? So this is 37 in the I direction. This angle over is 37, this is 53, 37, and then plus sine of 37 degrees in the j direction. Okay, so this is given by cosine in the negative I direction, and it's given by sine in the positive j direction. Okay, so cosine of 37 is negative 0.8, so it becomes negative 6.4. Okay, in the I direction. Sine of 36 is 0.6, so this becomes plus 4.8 in the j direction. All right, and that is meters per second. All right, so delta P equals mass times B final minus B initial. Okay, so that's 0.2. First let's write VF. VF is this one, negative 6.4 in the I, negative 6.4 in the I, plus 4.8 in the J, plus 4.8 in the J, and then we're going to subtract VI. VI is 8 in the I, 8 in the I plus 6 in the J, plus 6 in the J. Okay, so we've got 0.2. We're going to combine i's with i's, j's with j's. So negative 6.4 minus 8 is negative 14.4. So we've got 14.4 in the I direction. And then we've got 4.8 minus 6, that is plus 1.2 in the j. Okay? No, minus this one, minus 1.2 in the j. All right, and then of course we can multiply by 0.2, that is negative, we've got 2.88 in the I direction, and then this would be minus 24, that's 0.24 in the j direction. Okay, So this is the change in momentum. All right, now let's say B, calculate the impulse impacted on the object during the collision. So we're looking for I, okay? We're looking for I, but we have already seen that I actually equals change in momentum, okay? So just this one. So I equals delta P, which is negative 2.88 in the I direction minus 2.4 in, no, 0.4 in the J direction. All right, that is kilogram meter per second. All right, see if the object was in contact with the wall, let's say for 0.2 seconds, calculate the average force exerted on the object by the wall. Okay, so we're looking for the average force. Now force equals the rate of change of momentum with respect to time. Okay, if you want the average force, you would integrate this with time, maybe from t to t plus delta t, and then divide by delta. This is the average of this expression. Okay, but this one, so dt equals dt is just delta p. So average force is simply the change in momentum divided by delta t. Okay, so we already have delta t, and we're told delta t is 0.2 seconds. All right, so the average force is delta p, which we already calculated over here, which is negative 2.88 in the I direction plus 0 minus 0.24 in the J direction. 0.24 in the J direction divided by 0.2. Okay, so this will be negative 14.4 in the I direction minus will be 1.2 in the J direction. Okay, so that'll be the force acting on the object, newtons. All right, now we're going to look at the principle of conservation of momentum. Principle of conservation of momentum. Okay, I'm going to state first and then we improve it. Okay, so this principle said that if the net force acting on an object is 0, then its momentum is conserved. Momentum is conserved. Okay, that means the final and initial momentum are equal. This implies the final momentum equals the initial momentum. All right, so let's try to prove it. We're going to start from the statement of Newton's second law in terms of momentum. That law says the net force acting on an object equals the rate of change of momentum with respect to time. Okay, so if F net equals 0, that implies dP by dt is 0, or dP is equal to 0. Now if you integrate both equations, you get the integral of dP, which is delta P, okay, equals 0, okay? But delta P is P final minus P initial equals 0. So it follows that if the net force acting on an object is 0, then momentum doesn't change. Momentum remains the same. Okay. Now, momentum is usually used in relation to collisions. So let's look at conservation of momentum in collisions. Conservation of momentum in collisions. Conservation of momentum in collisions. Okay. Now suppose you have two objects colliding. Let's say this is object A, and let's say this is object B. Okay, so they collide. Both are going to exert force on each other, right? So let's say this object exerts this force over here. Let's call that the force on A by B, and this also will exert force. Okay, and that force let's call F on B by A. Okay, so these two forces are action-reaction forces. Okay, FAB and FBA are action-reaction forces. Action-reaction forces, which means the two forces are opposite. Newton's second law says that for every action there is an equal reaction, an equal opposite reaction. So what that means is FBA is actually the negative of AB. Okay. Now if you consider only this force, this object, there's a net force FBA acting on it. If you consider only this object, there's a net force FAB acting on it. How about if we treat both objects as a single system? Okay, if both objects are treated as a single system, then the net force is the sum of these two forces. Okay, then F net, the net force acting on the system, is the sum of these two forces, FAB plus FBA. Okay, but we know that this is negative FAB, so this equates to 0. So the conclusion is the net force acting on colliding objects is 0 if they're treated as a single system. So the conclusion is if colliding objects are treated as a single system, the net force acting on them is 0. The net force acting on them is 0. So it follows that the momentum of colliding objects is conserved. Therefore, momentum of colliding objects is conserved. momentum of colliding objects is conserved. Okay, so that means is the momentum before collision equals to the momentum after the collision. Now the momentum of the system is the sum of the momentums of the two objects, right? So P initial equals the sum of the momentum of object 1 plus momentum of object 2, okay? And P final equals the sum of the momentum of object 1 after collision plus the sum of object 2 after the collision, okay? So this implies the sum of the momentums before the collision equals the sum of the momentums after the collision. So you've got P1i plus P2i equals P1f plus P2f, okay? But we know that momentum equals mass times velocity, right? Suppose let's say this is the m1. Suppose let's say this is m2, okay? Suppose let's say this is the velocity of the object before the collision. Let's say this is the velocity of the second object after the collision. Maybe after the collision, maybe let's say this goes this way, so it will be the momentum of object 1 after the collision. Let's say this one goes this way, this would be the momentum of the object after the collision, okay? So using the formula momentum equals mass times velocity, this equation turns into following: m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f, okay? So this is the equation of momentum for colliding objects, okay? So as you can see, this is a vector equation, so normal will have both x and y components, but we'll deal with two-dimensional problems later. Now we're going to specialize to one-dimensional problems, okay? For a one-dimensional case, so let's look the one-dimensional case, that is collision in a straight line, the one-dimensional case, okay? This is collision in a straight line, collision in a straight line. So we can align our x-axis along the line of collision, and so we can take only the x component of this equation, okay? Because we're not going to have the y component if there's collision in a single line. So if you just take the x component, this becomes m1 v1ix plus m2 v2ix equals m1 v1fx plus m2 v2fx. So we don't have y component in this case, but since we have only one component, we don't have to include this x subscript over here. But just remember, in this formula, this velocities represent components, not magnitudes, okay? So this equation becomes m1 v1i plus m2 v2i equals m1 v1f m2 v2f, okay? Just remember, in this formula, these variables represent components, not magnitudes, where v1i, v2i, v1f, and v2f are components and not velocity, not magnitudes. Components, not magnitudes, okay? In other words, they can be negative and positive depending on the direction. They'll be positive if to the right, they'll be negative if to the left, okay? All right, so let's look at an example. let's say a 10 kilogram object moving with a speed of, let's say, 5 meters per second to the right. Collides, let's say, with a 1 kilogram object moving to the left, let's say, with a speed of let's say maybe 2 meters per second. Okay, now after the collision, the 10 kilogram object moves to the right, let's say with a speed of maybe 3 meters per second. So the question is, calculate the speed of the 1 kilogram object after collision. Okay, so let's call the 10 kilogram M1. So let's say M1 is 10 kilogram. Okay, and its initial speed is 5 meters per second to the right. Right means positive. Okay, so it'll be 5 meters per second. Okay, we're also told the 10 kilogram object moves to the right with a speed of 3 meters per second. So that is V1F. So V1F is 3 meters per second. Okay, now let's look at the second object. Its mass is 1 kilogram. So you've got M2 equals 1 kilogram. And its initial velocity is moving to the left, the speed of 2 meters per second. Now remember, left is negative, so it's going to be negative 2 meters per second. Now we don't know its velocity after collision. Okay, so that's the problem. So we're going to use the equation of collisions, that is M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Okay, so let's plug the numbers. M1 is 10, V1I is 5, plus M2 is 1, V2I is negative 2, equals 10, V1F is 3, and then M2 is 1. We don't know V2F. That's the question. Okay, so you've got 50 minus 2 is 48, equals 30 plus V2F. Okay, so it follows that the speed of the 1 kilogram object after the collision is 18 meters per second. Okay, all right. Now we're going to look at two kinds of extreme types of collisions. They're called completely elastic and completely inelastic collisions. So we're going to start with completely inelastic collision. Completely inelastic collision. Now this is a collision where the two objects stick together after the collision. Okay, the two objects stick together after the collision. Stick together after the collision. And in this type of collisions, energy is not conserved. Some of the motion energy will be lost during the collision. So we can say kinetic energy is lost during the collision. Kinetic energy is lost during this collision, during this type of collision. Okay, So it is characterized by two things. First of all, the objects stick together after collision, and kinetic energy is not conserved during this kind of collision because some of the energy will be converted to heat energy during the collision. Okay, so if the two objects stick together, what does this mean? Their velocities of their collision are going to be equal. Okay, stick together implies v1f equals v2f. Okay, let's just call it capital V. Okay, so let's go back to the general equation now. The general equation is m1 v1f v1I plus m2 v2I equals m1 v1f plus m2 v2f. Okay, but these two are equal, they're equal to capital V. Okay, so we get the following equation: m1 v1I plus m2 v2I equals m1 plus m2 times their common speed, capital V. Okay, so if you know the collision is completely inelastic, you can use this formula. All right. Now let's look at an example. Well, for one-dimensional problem, we'll just take off the vector sense. One-dimensional case, we're going to take off the vectors. Just remember the velocities represent components. Okay, so it will be m1 v1I plus m2 v2I equals m1 plus m2 capital V. Just remember the velocities are components, not magnitudes in this formula. All right. Example. Let's say a 5 kilogram object moving with a speed of, let's say, 4 meters per second to the right, collides with a 2 kilogram object moving to the left, let's say with a speed of maybe 2 meters per second in the same direction to the right. Okay, so if the collision is completely inelastic, calculate their speed, calculate their speed after collision, or their velocity after collision. Okay, so we have a 5 kilogram object, let's call it M1. M1 is 5 kilograms. Okay, initially it's moving with the speed of 4 meters per second to the right, so that's V1I. V1I is 4 meters per second. Okay, and then the second object has a mass of 2 kilograms. Okay, and it's moving with a speed of 2 meters per second to the right. Okay, that's 2 meters per second. So the question is find their common speed after the collision. And so since the collision is completely inelastic, we can use this formula over here. Okay, so we have the formula is m1 v1I plus m2 v2I equals m1 plus m2 times the common speed v. Okay, so m1 is 5, v1i is 4, m2 is 2, v2i is 2, equals 5 plus 2 times the common speed v. Okay, so we've got 20 plus 4 equals 7v. So it follows that their common speed is 24 divided by 7 meters per second. And it's positive. What does tell us? To the right. Positive means to the right. Okay. Now, a very good application of this kind of collision is what they call the ballistic pendulum. So let's look at the ballistic pendulum. Ballistic pendulum. This is a pendulum used to measure the speeds of bullets. Use it to measure the speed of a bullet. The speed of a bullet. Okay. Suppose we have the following pendulum. Okay. Let's say its mass is mp, and then we fire a bullet. Let's say its mass is mb with the speed of, let's say, vb. Okay. Now the bullet is embedded over here, and then it's going to swing. Okay, this is going to swing like this. And let's say it's the maximum height reached. This would be the maximum height reached after the collision. Okay, the bullet will be embedded, and so this will have kinetic energy. It has no way to go, so you're going to swing this way, and this is the maximum height it reaches h. Okay, so the question is to find expression for the speed in terms of this height. If you're able to do that, then we can just measure the speed of the bullet by just measuring the height to which the pendulum rises. Okay, so let's apply the equation for complete inelastic collision, which is the mass of the bullet, the speed of the bullet. Remember, the pendulum is initially at rest, so its initial momentum is 0, and then you've got the sum of the mass of the bullet, mass of the pendulum times the common speed v. Okay, because the bullet is embedded in the pendulum, they'll move together. All right, so that gives us a formula for the speed of the bullet, which is mass of the bullet plus mass of the pendulum divided by the mass of the bullet times their common speed after collision. Okay, now we know that after the collision, this will serve the speed capital V and then rise to this height over here. So this means is the kinetic energy the object has at the bottom location over here will be completely converted to gravitational potential at this location. So you can say that the kinetic energy at this location is equal to the gravitational potential energy at this location, because mechanical energy is conserved. Okay, over here, if we put our coordinate system over here, we have 0 potential energy and kinetic energy, and over here at the maximum height, the speed will be 0. We have 0 kinetic energy and potential energy, so the initial kinetic energy equals the final potential energy. Okay, so using conservation of mechanical energy, using conservation of mechanical energy, so the mechanical energy at the bottom equals mechanical energy at the top. Okay, so that is kinetic energy at the bottom plus potential energy at the bottom equals kinetic energy at the top plus potential energy at the top. Okay, so if you put our coordinate system at the lowest point, this potential energy is going to be 0. Okay, and at the maximum height the speed is 0, so this will go away. Okay, so kinetic energy at the bottom equals potential energy at the top, but the kinetic energy at the bottom is half of mass of bullet plus mass of pendulum times v squared, and the potential energy at the top is mass, which is the sum of both masses, and then times gravitational acceleration and times h, the height which it rises. Okay, so you see the mass cancels out. Okay, so we have the following formula: the square of the velocity equals 2 times gravitational acceleration times height, and then it follows that the speed just after the collision is the square root of 2gh. So if you put that right over here, what do we get? The speed of the bullet equals mass of bullet plus mass of pendulum divided by mass of the bullet times the square root of 2gh. Okay, so to calculate the speed of the bullet, all I have to do is measure the height to which the bullet, the bullet pendulum system rises, and with that we can calculate we can measure the speed of the bullet.